So now that we've finished off talking about the leading coefficient test and talking about zeros and multiplicities of zeros and how that influences the graph, let's put all of that to use to begin sketching some polynomial functions. All right, here we have our first example. Sketch a graph of the polynomial function f of x is equal to x to the fourth minus x cubed minus 20x squared. Whenever you are sketching polynomials, the first thing that you want to do is apply the leading coefficient test. Okay, again, the leading coefficient test tells us the end behavior of the graph. What does it do as it goes to the right, and what does it do as it goes to the left? To apply the leading coefficient test, we must look at the degree of the polynomial and the leading coefficient. All right, notice the highest power of x in this case is x to the fourth. This is our highest power term right here. Our degree is 4, and our leading coefficient is positive 1. That means we have an even degree, 4 is an even number, and a positive leading coefficient. Even degree and positive leading coefficient, that means that our graph is going to rise to the left and also rise to the right. Okay, even degree and positive leading coefficient rises to the left and rises to the right. After we apply the leading coefficient test, we want to find the zeros of our polynomial. Well, how do we find zeros of a polynomial? We set the function equal to 0. 0 is equal to x to the fourth minus x cubed minus 20x squared. To find zeros of polynomial functions, we are going to have to be able to factor. Make sure that you are comfortable with all types of factoring. Again, if you're struggling with factoring at all, make sure you reach out for extra help. When we go to factor, the first thing we want to look for is a greatest common factor. In this case, I can begin factoring the polynomial by factoring out a greatest common factor of x squared. Factoring out an x squared, that leaves me with 0 is equal to x squared times x squared minus x minus 20. Now I can continue to factor this quadratic portion of the polynomial. All right, x squared minus x minus 20, that is going to factor into x minus 5 times x plus 4. This leaves me with x squared times x minus 5 times x plus 4. And now that this is completely factored, we can set each one of the factors equal to 0. Notice setting x equal to 0, well, that gives me my first 0. That's just x equals 0. Setting the next factor equal to 0, x minus 5 is equal to 0, and solving for x gives me x equals 5 as my next 0. And setting my final factor of x plus 4 equal to 0 and solving for x gives me x is equal to negative 4. These are my 3 zeros. And once we identify the zeros, we need to determine the multiplicity of each zero. In other words, how many times does each zero occur? Well, x equals 0 comes from our factor x. How many times does that factor occur? How many times does this 0 occur? Well, notice this is derived from x squared. That would be x times x. So the multiplicity of this 0 is 2, and 2 is an even number. Right? Even multiplicity means that our graph is going to bounce when it hits x equals 0 along the x-axis. What about the multiplicity of x equals 5? How many times does this factor or this 0 occur? Well, this factor only occurs one time, which is odd, which means that the graph is going to go through the x-axis at x equals 5. And our final 0, x equals negative 4, this factor and this 0 only occur one time as well. Odd multiplicity, meaning that it is going to go through the x-axis at that x-intercept. All right, now we have enough information to sketch our graph. Start by drawing out your coordinate plane. After you draw your coordinate plane, begin by plotting the zeros, okay, the x-intercepts. We have x-intercepts at negative 4, we have an x-intercept at 0, and we have an x-intercept at 5. Okay, after you plot the zeros, think about the end behavior of the graph. What does this graph have to do on either side of my final zeros? Well, I know that this graph has to go up to the left and that the graph has to go up to the right. All right, I can include that component of the graph. It goes up to the left and up to the right. That is my end behavior. Now, let's think about what is going to happen as we get to each one of these zeros. Well, if I'm coming from up to the left, I'm coming down to x equals -4. I know that this zero has an odd multiplicity of 1. Odd multiplicity of 1 means that my graph is going to go straight through the x-axis at -4. All right, so I can draw in that component of the graph. Now, at x equals 0, I have even multiplicity. So that means my graph must turn and come back up, and that because the multiplicity of x equals 0 is even, it is going to bounce when it hits the x-axis. All right, so it's going to turn around again. Again, even multiplicity means that the graph is going to bounce. And now as I continue along the graph and get to my final 0, we know that the multiplicity of x equals 5 is odd. Therefore, it is going to cross through the x-axis at x equals 5. All right, and once we have all those pieces of information, we can connect our lines and connect our dots with nice smooth curves, and that will give us our final graph of the polynomial function. All right, and so here we have the sketch of f of x equals x to the fourth minus x cubed minus 20x squared. Now, you're probably wondering, how do I know how far down this graph is going to go? Well, to be honest with you, in this class, you don't. All right, so if your sketch doesn't look exactly the same as this, all right, maybe yours looks more like a W, that is perfectly acceptable. Next year, however, when you take calculus, you will learn how to figure out where these relative minimums are occurring, and that will be able to give you a more complete sketch. All right, notice that I haven't even bothered to label the y-axis here. I'm not worried about your y-axis scaling at all. The key things that I'm looking for is, do you have the correct zeros? Do you have the correct end behavior? And do you have the correct behavior around each one of the zeros? That is all you need to get full credit on your sketches. All right, let's take a look at another example. Sketch a graph of the polynomial function f of x is equal to x cubed plus 3x squared minus 4x minus 12. As we said, always begin with the leading coefficient test to determine the end behavior of the function. All right, we identify our highest power of x. All right, that term is 1x cubed. We have an odd degree polynomial with a positive leading coefficient. What does that mean? Odd degree, positive leading coefficient. That means our graph is going to fall to the left and rise to the right. All right, there we have our end behavior. Next, after we apply the leading coefficient test, we want to find the zeros of our function. Well, how do we find the zeros of a function? We set the function equal to 0. 0 is equal to x cubed plus 3x squared minus 4x minus 12. Again, whenever you go to factor, look for a greatest common factor first. In this case, there is no greatest common factor for us to factor out. So, how can we factor this cubic polynomial? Well, this is actually one that will require us to factor by grouping. Hopefully you recall factoring by grouping from your Algebra 2 classes last year. What does factoring by grouping mean? Well, that means we want to group two of our terms together, all right, two pairs of terms together, and factor out a greatest common factor from those two terms, hopefully resulting in a common value inside of each parentheses. Let's see if we can do that. So let's group our first two terms and our last two terms. I have x cubed plus 3x squared plus a negative 4x plus a 12. You guys agree that if we were to add a negative 4x and to add a negative 12, we would just end up with our original equation that we started with up here. All right, so we've grouped our first two terms and we have grouped our second two terms. Now, factor out a greatest common factor from each grouping. Notice our greatest common factor from the first grouping is going to be an x squared, and our greatest common factor from the second grouping is going to be a negative 4x. That leaves us with x squared times the quantity x plus 3 minus 4 times the quantity x plus 3. All right, whenever you factor by grouping, the goal is to create the same values inside of your parentheses. Notice in this case, we have an x plus 3 and an x plus 3. That is a good thing. All right, if that is the case, that tells you what the factors are. The factors are going to be the combination of the coefficients in front of your groupings. All right, so one of my factors is going to be an x squared minus 4. And my other factor is going to be just what that grouping is, x plus 3. Okay, this factors into x squared minus 4 times x plus 3. Notice my first factor is the pairings of the coefficients, x squared and negative 4, and my second factor is what I had remaining inside of the parentheses. All right, so if you have questions on factoring by grouping, make sure you talk to me. Now, is this completely factored? Well, we can actually factor this quadratic a little bit farther. Here I have x squared minus 4. That is the difference of squares. That factors into x plus 2, x minus 2. And again, I still have my x plus 3 here on the outside. So now that it is completely factored, we can identify the zeros of the polynomial. The zeros are x equals negative 2, x equals positive 2, and x equals negative 3. Again, we get those by setting each of the factors equal to 0 and solving for x. Once we find the zeros, we need to identify the multiplicity of each zero. In other words, how many times does each zero or each factor occur? Well, in this case, each factor and each zero only occur once. That means each one has an odd multiplicity of 1, and an odd multiplicity of 1 means that the graph is going to go through the x-axis at that 0. So now we have enough information to sketch our graph. All right, begin by drawing out your coordinate plane and plotting your zeros. We have a 0 here at negative 3. We have a 0 here at negative 2, and we have a 0 at x equals positive 2. All right, plot those zeros. After you plot the zeros, look at your end behavior. What does the graph do as it goes to the left, and what does it do as it goes to the right? We know that this graph has to go down to the left, and it has to go up to the right. So we can apply that end behavior, down to the left, up to the right. And what has to happen at our zeros? Well, we said each one has an odd multiplicity of 1. That means it's just going to go straight through at that x-intercept. So that means I have to come from down here. I have to go up and straight through that first one. And that means I would have to then come down and straight through my second 0, which would then require me to come up and straight through my third 0 at x equals 2. All right, so we can play connect the dots now in our lines to finish off our sketch of our graph. There we have the graph of f of x equals x cubed plus 3x squared minus 4x minus 12. Now, again, are you going to know how far down this graph dips or how far up this graph goes to this relative maximum? No, and I know you're thrilled to see it. You'll have to be patient and wait till next year in calculus. All right. So again, you'll notice no scaling on my y-axis. I'm not worried about how far down or up it goes, just that you have the proper zeros, the proper end behavior, and the proper behavior around each one of those zeros. All right, one more final example here. Sketch a graph of the polynomial function f of x is equal to x minus 3 cubed times x plus 2 squared times 1 minus x. Now, you might notice that this polynomial is actually written in factored form, okay? It hasn't been expanded. So factored form is nice in that it makes it really easy to find the zeros, right? All we have to do is set each one of the factors equal to 0, but it does make it a little bit more challenging in terms of applying the leading coefficient test, right? So to apply the leading coefficient test, we need to figure out what the highest power of x is going to be, as well as the constant multiple or leading coefficient that comes in front of it. To do so, we have to analyze each of the individual factors. All right. Again, we don't want to have to multiply all of this out. That would be a real pain. But we can figure out what the highest powers of x for each one will be. Notice if I were to multiply out x minus 3 times x minus 3 times x minus 3, right? That's x minus 3 quantity cubed. My highest power of x from this grouping would be x to the third. For this grouping, x plus 2 quantity squared, if I were to multiply x plus 2 times x plus 2, my highest power of x would be x squared. And for my final grouping, well, my highest power of x is just going to be negative x. Pay careful attention. Make sure you include negatives if they are necessary. So, what would happen if we were to multiply all of these together? Well, whenever we multiply exponential quantities with like bases, we need to add the exponents. Here I have an exponent of 3, an exponent of 2, and an exponent of 1. Adding those exponents is going to give me 6 as my power, but notice that the leading coefficient is actually going to be negative. I've got a positive 1 times a positive 1 times a negative 1. So this leaves me with negative x to the 6th. Okay? This would be the most powerful term of this particular polynomial. All right, so this is a polynomial of degree 6, and it has a negative leading coefficient. Even degree and negative leading coefficient, well, what does that mean? The graph is going to fall to the left and fall to the right. All right, so after we apply the leading coefficient test, we need to determine the zeros. Again, to find the zeros, we take the function and we set it equal to 0. 0 is equal to x minus 3 quantity cubed times x plus 2 quantity squared times 1 minus x. To find the zeros, we set each one of the factors equal to 0 and we solve. Solving for our first factor, we get x is equal to 3. Our second factor gives us x is equal to negative 2. And our third factor will give us x is equal to 1. Once we identify the zeros, we need to determine the multiplicity of each zero. How many times does each zero occur? Well, notice that this factor, x minus 3, occurs 3 times. X minus 3 quantity cubed is x minus 3 times x minus 3 times x minus 3. So that 0 has a multiplicity of 3, which is an odd number. Our next factor occurs twice, right? It's x plus 2 quantity squared. That means that the 0 x equals negative 2 has a multiplicity of 2, which is an even number. And finally, our last factor, well, this one only occurs one time. Therefore, our 0 has odd multiplicity of 1. Once we have all that information laid out, we can begin to sketch our graph. We draw out our coordinate plane and start off by plotting our zeros. Notice we have a 0 here at x equals negative 2. We have a 0 here at x equals 1. And we have a 0 here at x equals 3. Plot those zeros. After you plot the zeros, think about the end behavior of the graph. What does this graph have to do? Well, it has to fall to the left and it has to fall to the right. Okay, so put in that behavior. Now, let's think about what happens as we approach each one of these x-intercepts. So here at negative 2, I have even multiplicity of 2. Remember that even multiplicity is going to cause the function to bounce at that x-intercept. In other words, it's going to hit the x-axis and turn and come back around. All right, so my graph has to come up, hit negative 2, and turn. Next, our next 0 is x equals 1. That is an odd multiplicity of 1, which means that our graph is going to go straight through. That would mean that my graph would have to turn from here and start to come up and go straight through at x equals 1. And then our final 0 is x equals 3, which has an odd multiplicity, which means that it's going to go through the x-axis. But remember that when you have odd multiplicity that's greater than 1, it is also going to create an inflection point. Notice that this will behave just like an x cubed. So what does that mean? The graph is going to come down and through x equals 3, but it will flatten out in the process. All right? We have our inflection point here at x equals 3. The graph flattens out as it goes through the x-axis. And now that we have all of that information labeled out with our inflection point at x equals 3, we can play connect the dots and the curves, complete our sketch with nice smooth curves. Here we have the graph of f of x is equal to x minus 3 cubed times x plus 2 squared times 1 minus x. Again, the y-axis, no scalings on the y-axis. I'm not worried about how far down your graph goes or how far up your graph goes. Again, I am looking for the end behavior, that you have the proper zeros, and that you have the proper behavior at each zero. All right, make sure you guys label any inflection points. There we have sketching graphs of polynomial functions. If you have any questions, be sure to reach out for some extra help.